The mole. Chemists have needed a method to convert from measurements made on the macroscopic scale to the models of matter that exist on a very, very different scale, the atomic scale. Fortunately, we have the mole. The mole helps us go from the macroscopic measurement to the models on the microscopic scale. This hasn't always been the case, of course. As this science of chemistry evolved in the early 1700s, what chemists did to study matter was very carefully weigh stuff. Weigh stuff as it underwent a chemical change. Weigh it again after the change. Weigh stuff as it went through a physical change. Weigh it again before and after, and compare those differences in weights. And as they were doing this in the 1700s, the models were developing as to how things were changing, the relative mass scales of the different elements that they were creating. And so they started developing models to explain what they were experiencing in the lab. And the models to explain how stuff was changing led us to the atomic theory very early on in the 1800s, and it was fully developed in the 1900s. So we still live in the macroscopic world, even though we know a lot about the microscopic world, and so we're constantly having to go back and forth between what we see and what we can measure on the macroscopic scale and the models that allow us to predict and understand what's happening on the macroscopic scale. And those models are the atomic model and the chemist's view of the world. Okay, so we need a way to go back and forth between the macroscale and the microscale. Well, as it turns out, early on, as the scientists were becoming to understand in the 1700s the matter and how it changed, they developed a mass unit type of a scale. All the elements that they were discovering in the compounds, they could relate on this kind of relative mass unit scale. And what they found was that hydrogen was the lightest element, and so it was assigned a value of 1 atomic mass unit. Oxygen was about 16 times heavier, so it's 16 atomic mass units. Carbon, about 12 times greater, 12 atomic mass units. So we have this relative scale for the smallest bit of matter, which was becoming to be known as the atom, and some kind of relative scale. All right, but it's very, very tiny, so we need a very, very big number to relate that tiny model to the macroscopic scale. And that big number is 6.022 times 10 to the 23rd. That's the number that we call the mole, 6.022 times 10 to the 23rd. Well, why did we choose that big number to relate the macroscopic world with the microscopic world? Well, that's because 6.022 times 10 to the 23rd is the number of carbon-12 atoms in 12 grams of carbon-12. Carbon-12 is an isotope of carbon that has a mass number of 12, 6 neutrons and 6 protons. And so it turns out that this number, 6.022 times 10 to the 23rd, that's the number of atoms that weighs 12 grams. And so therefore we say 1 mole of carbon-12 weighs 12 grams. And because there was already this relative scale, then that means that 1 mole of hydrogen weighs 1 gram. 1 mole of oxygen weighs 16 grams. So we're able to define now a mass scale that can be related to the number of particles that exist in that particular mass. Okay, so here's some examples of a mole of various pure substances. This is a mole of copper, and it happens to weigh 64 grams. In this small beaker is a mole of aluminum, weighing 27 grams. Here we have a mole of sulfur, and it weighs 28 grams. Let's skip over here. What is that? That's water. And that is 1 mole of water, and it weighs 18 grams. Over here, that's copper 2 chloride, and it weighs 135 grams, 1 mole of it. All right, so you can see, 1 mole of these various pure substances weigh these various masses, and those are called the molar masses, and you can see about how much of each one of those that you have. Now, what about 1 mole of let's just say a pencil eraser. how much space would 1 mole of a pencil eraser take up? If 1 mole of water takes up, oh, it looks to be about 20 milliliters, 18 milliliters of volume. What about 1 mole of pencil erasers? Well, as it turns out, 1 mole of pencil erasers, just your average pencil eraser on the end of your number 2 pencil, well, that 1 mole of those pencil erasers would cover the surface of the earth to a depth of 500 meters. Okay, so the mole is only a convenient unit of measure for very, very, very tiny things. It brings up the mass of those very, very tiny things to a place on a scale that we can see, say, on a lab bench. But 1 mole of anything else is beyond comprehension. All right, so the mole, 6.022 times 10 to the 23rd. Why is it also called Avogadro's number? Well, it's called Avogadro's number because Avogadro didn't come up with the number, but he was a scientist working very hard in the 1700s on some way of relating the number of atoms of elements to the amount of atoms and elements. He was the one who came up with the relationship between the mass, and he predicted that scientists would come up with a number that could very easily relate on the gram scale the number of moles, or excuse me, the number of particles for given mass units. So he gets the name associated with it. Now, the abbreviation for the mole, sometimes you'll see it abbreviated MOL. That's a common abbreviation for the mole when it's found in units, next to units. Also, in equations, when you're referring to the number of items in a mole, or Avogadro's number, sometimes it's a capital N with an A next to it. That's another way we abbreviate Avogadro's number, 6.022 times 10 to the 23rd. And another way that we abbreviate, well, Avogadro's number really means 6.022 times 10 to the 23rd of something. And another way we abbreviate within formulas the number of moles is the lowercase n. So you'll see these various representations of the mole depending on the equation and what you're working on. Do you need to memorize this number, 6.022 times 10 to the 23rd? Yes, you do. It's very important. It's worth memorizing. How will you use the number? Well, because we're always flipping back and forth between thinking macro, thinking micro, you'll use the number in a variety of ways. Someone might ask you, for example, how many carbon dioxide molecules are there in 2 grams of carbon dioxide. All right, and if that's the case, if they want to know the actual number of molecules, then you're given a mass, then you're going to have to convert from the mass of the carbon dioxide to the moles of carbon dioxide to the number of molecules of carbon dioxide. Okay, and so to do that, you would need to use the molar mass of carbon dioxide, and then you'd have to use Avogadro's number to convert from the moles to the number, and that is that 1 mole equals 6.022 times 10 to the 23rd. Okay? The molar mass of carbon dioxide, how do you figure that out? Well, you look at the periodic table, and you find the molar mass of carbon, which is 12 grams per mole, and the molar mass of oxygen, which is 16 grams per mole. And of course, there's 2 of those. So it would be 12 plus 2 times 16 is 44 grams per mole. So we have a way to convert from mass to moles to actual number of molecules.